from their papers and patents and web pages, newswire, even press releases, tweets, and blogs. We'd like to accelerate the progress of science by doing this, and you can imagine some ways in which this would be helpful by helping people find papers to read and to cite, or find reviewers or collaborators or people to hire. I'm always trying to find new postdocs, and I would love to have a tool like this to help me do so, or even policymakers to understand trends and the landscape of science. Okay, so to do all of this, we need to do some information extraction from text into large databases, and let's look at how that's done. Look at it just in pictures without equations. All right, so we start with some text, and one of the first things we need to do is find mentions of those entities, like Wei Li and Tsinghua University. All right, and then we can also find relations in the midst of this text, like Wei Li attends Tsinghua University. And then Wei Li might appear in many places in the text, but she might also be in some structured data that we already have sitting around, and we'd like to incorporate that as well. And now there are many appearances of Wei Li appearing everywhere, and I'd like to pull them together by resolving them, or doing entity resolution or co-reference, to know when we're talking about Wei Li is the same person and when actually Wei Li is a different person. And we try to do that from using all kinds of machine learning and methods. And then here I have what we think about as the truth about entities and relations. I put this into my database from which I can answer queries. And the machine learning community takes great pride in having made a lot of progress just in the last 10 years over doing these things much more accurately than was available before. But it's 90% isn't perfect. And although 90% might be OK as an individual item, the errors snowball through this chain, right? Once you make an error early in the chain, it's very hard to recover from it later. And so the end accuracy is more like taking 0.9 and raising it to the third power, which doesn't look so good. So in response to this, I and others have been interested in reasoning with more uncertainty and sort of joint reasoning throughout this process by reasoning about probability distributions over possible outputs, not passing just the single most likely outcome, and reasoning with sort of top-down and bottom-up reasoning so that later more global thinking can help correct errors in my low-level thinking. And so you can think about this as reasoning about all of these together, and we call it joint inference. And we and others have shown that it absolutely can make a large difference in the accuracy of these systems. Most of this past work has been joint inference at the early steps of this pipeline, where we're reasoning jointly about, say, the data that falls in one sentence, or maybe within one document. But I actually think that there's more juice to be had by reasoning at the far end of the pipeline, because that's just where we have more data that we've marshaled all together from which we can share evidence and look for more patterns that can help us remove errors and confirm patterns. But joint inference was hard enough at the early stages of the pipeline as it is, and now I'm going to try to reason with uncertainty about more random variables than I can even fit in memory. And that presents a whole new challenge. And so this has us thinking about these problems in a bit of a different way. But first, let's consider some of the interesting issues that this brings up. So how am I going to represent and inject uncertainty from extraction into the database? I'd like to use the database's contents to help me do a better job of information extraction. This is like the way that we all use our innate common sense knowledge or knowledge about the world when we're interpreting low-level language. And third, and maybe this is the most salient in practical terms, extraction is not one shot. It's not like I'm going to have my 200 million documents, extract from that, and then I'm done. Tomorrow I'm going to have another 10,000 documents, and the new evidence that I receive tomorrow should sometimes cause me to change my mind about something I extracted yesterday. Like, oh, I thought these were two different people, but now I see with this new data, they're actually the same person. And so I would like the database not just to store the results of the truth in the end, but help me manage the whole information extraction pipeline, storing intermediate results that help make it easier for me to go back and backpatch these situations. So with that in mind, we've been thinking about enlarging the purview of the database to look more like this, in which the database stores all of those intermediate values. And the only thing that you really inject into the database is not the result of some external truth discovery process. It's just the raw evidence. And it's up to the database internally to discover its own notion of the truth. So I think of this as aligned with epistemological philosophy, which says, you don't get to observe the truth, right? You just observe your evidence, and it's up to your own reasoning to discover the truth. So we've taken to calling these epistemological databases. And before moving on and getting to FACTORIE, let me just briefly describe some implications of what this looks like. starting with human edits. So you build a large knowledge base. Whether it's built automatically or by humans, inevitably it's going to have some errors in it. And when your human users look at it and they notice some errors, they're going to feel better if they have the opportunity to make some corrections. And the classic way to manage this, think about Wikipedia, I suppose, is a human edit consists of going into the place where the truth is stored, erasing the old value, writing in a new value, and maybe you keep some edit history so you can know some provenance so you can unroll it if you want. But this is really unsatisfying because users may have edit wars, and also sometimes the human can make a correct edit, but then the state of the world changes 6 months later. Automated extraction notices the change, but the human didn't, and so sometimes the automated method should be allowed to overwrite the human. And so with this in mind, we've taken to thinking of a human edit as just like an additional piece of evidence. It's like a little mini document that says, on this date, Scott said that this thing was true, and that evidence just participates along with the rest, including the textual data in part of this truth discovery process, in which we can balance all these pieces of evidence, reason about truth and about human editors' reliability all at once. We also then do a lot of work on never-ending inference. So the truth isn't discovered just once externally, but there's some sense in which inference is constantly bubbling in the background inside the database, always being reconsidered with more evidence, more time. There will be also times when our database has some holes in it, and we'd like to fill them in with additional data, and we think it's probably out on the web somewhere, but we don't quite have Google-sized resources to extract from the entire web. So we'd like in some targeted way to go out and do queries to find exactly the raw data that we think might be able to best help us fill our particular holes. And this actually turns into a reinforcement learning problem that we've done some work on. And then furthermore, and lastly, if we're going to do this at large scale, we have to think in with parallelism in mind. And we have found that just using MapReduce as a black box is often a really bad idea, and have seen some great gains by reasoning in a tightly integrated fashion about the details of machine learning and the way parallelism works, and have gotten some big wins there, as have GraphLab. I know there's some folks from GraphLab here tonight. All right. So with that, now let me jump into FACTORIE. So FACTORIE is a tool that's going to help us do a lot of these things as well as other stuff. And so FACTORIE is it's probably like the 5th major machine learning toolkit that I've built over the last couple of decades. I won't bother to tell you about the first 2. The third one that I built was actually at this startup company in the late 90s. It was the core intellectual property of the company. It consisted of about 300,000 lines of Java, and it did classification and clustering and confidence and finite state transducers and various things like that. And when the company went up in flames, it got locked in a closet and never to be seen again. And I decided to go to the university. I mean, I liked the startup life. I had a lot of fun, and I might do it again, but I missed working with students and doing research, and so I wanted to go to the university, and I arrived at UMass, and I knew that to do the kind of research I cared about, we'd need a lot of infrastructure, and that's when I set off to build Mallet. It's grown since then to about 130,000 lines of Java. It's pretty widely used both in industry and academia, and it does classification, sequence labeling, and a little bit of topic modeling. And if those are the things you care about, then that was great. But our research was heading us in even more general directions. They weren't covered by these cases. And around 2006 or 7, I was also feeling a little bit tired of the verbosity of Java. And so I talked to one of my programming languages fellow faculty members who recommended that I talk with Martin Odersky. And this got me interested in Scala. So so this was around late 2006. I started working in Scala, started working on the precursor of FACTORIE, got something up and running that was already supporting our research in about 6 months, wrote email to Martin around the middle of 2008, and he says, thanks for your mail. I'm excited that Scala finds some following in the machine learning community. At first, it seemed surprising because I thought that machine learning demands very conservative resource usage, in particular memory, and that therefore C++ would be more suitable. But I think what we've all found is that, number one, in machine learning, having a kind of degree of flexibility and composability can be really important, because people often don't build cookie-cutter models but want to put them together in different ways. And that secondly, something that runs in the JVM is not, not necessarily that slow. And furthermore, actually, the biggest speed gains can also be made by algorithmic differences and not necessarily low-level considerations. And we've certainly found that ourselves in some ways that I'll actually describe later. OK, so FACTORIE is not that big right now. I don't know, about 60,000 lines of Scala. It's used at several universities and a few companies, and not as widely as Mallet yet. And unlike Mallet, it's designed to handle arbitrary factor graphs. I'll talk about factor graphs in a minute, but they're essentially the generalization of both directed and undirected graphical models. Or graphical models, I think of them as the lingua franca of machine learning. Most kinds of machine learning can be expressed as a graphical model. It does all kinds of general inference and optimization in these models. It can be used for all kinds of applications, but since we ourselves do a lot of work in natural language processing, it has extensive pre-built natural language processing tools. It also does some topic modeling, and actually in a way that's faster than Mallet's now, and also the kind of word vector building that the Google Brain team has been doing. Some of the simpler versions of that have been implemented in FACTORIE as well. OK, so first I want to make sure that we're all on the same page about what a factor graph is, because it's the key basis on which the rest of FACTORIE is built. So let's start with a short tutorial on that. And let's start with a simple task, and that's just item labeling or classification. Let's say we want to do spam filtering. So what does our data look like? We have a collection of email messages. And because we're going to be talking about probabilistic models, all of our data is going to be captured as a random variable. This is an observed random variable. We're given this. We know what its value is. It's some collection of text. Our other random variable is the label that we're trying to produce. This is the predicted random variable associated with each spam messages I'm trying to say. Is it spam or not spam? And how am I going to accomplish this? And the observed email message and produces some real valued score, where higher scores say I find these values more compatible. And these black boxes we'll call factors. Right? So again, a factor is like a compatibility function, a function that takes as its arguments the values of the variables to which it's connected through these edges, and it's responsible for returning just a real value. And so this is a factor graph. And probabilistic inference then consists of going to the variables whose values you're supposed to predict, considering all their different values, finding the one that gives you the highest score, and then that's the one you say is the preferred one according to the model. All right, so here's one simple one. Let's consider another task, Chinese word segmentation. Because Chinese doesn't come with spaces between the words. If we want to do natural language processing, we need to find those boundaries ourselves. So our observed data are, again, the Chinese characters in sequence. We're trying to predict which character is the start of a word and which one is not the start of a word, in the middle or the end of a word. And we could build a model like this that measures the compatibility between individual Chinese characters and whether we think it's the start or the middle or end of a word. But this actually is not so great, because there are really strong dependencies, sequential dependencies among the labels. Whether I think that this thing is a not start label may depend on what label I gave to the previous character. And so I should add some compatibility functions like this. These correspond to the transition probabilities in the Hinabarkov model. Yes?
Sorry, Chinese may be not the hardest language for segmentation. Did you try Thai?
So let's see, I'm not an expert in these things. I did at one point build a Chinese word segmenter. I believe you that Thai is harder. Yeah, absolutely. Yeah. OK, so here's a more complicated factor graph. Inference now just became more difficult, because before, when searching for the highest scoring configuration, I could look at each variable independently and just cycle through the two options, find the one that scores the best, and then move on to the next. But now they're all interconnected. And although one particular choice might be locally the best for this one character, it might not be best in the interconnected chain. And so naively, I need to search through all possible combinations of the entire sequence to find the one that scores best. And there are 2 to the 4th of them here. And in a sentence of, say, length 20, there would be 2 to the 20th. That sounds pretty bad. But luckily, there are efficient dynamic programs that will find the exact solution in much less time than that. OK, so now you know what a factor graph is. So However, we care about models that are much more hairy than this. So like we look at problems like information integration. Like we have 300 hospitals and that all have databases in their own schema, patient databases. We'd like to pull all those together into one schema so that we can do some analysis of pattern analysis of patient outcomes. So we need to align the columns of these tables with each other. We need to align the rows of these tables with each other. And we need to decide what's the canonical value that we're going to put into the cells once we get all this alignment done. And we also build graphical models for doing this, for doing, say, the coreference and canonicalization. And we build other graphical models for doing the schema matching. And then actually you can do a much better job if you don't do these sequentially, but do them all together in one big joint model in which you're kind of simultaneously doing row and column matching at the same time. And it gets really hairy. And this brings up all kinds of really juicy scientific machine learning problems in parameter estimation and inference. But besides this, even just the software engineering is hard. And my students were finding this. We'd have some new idea about some probabilistic model we wanted to try. And it would take 2 months for us to implement it and get it debugged and get the results. And of course, the nature of research is that you try one model and then you have another idea tomorrow and you want to try another model. And it was really slowing down our research. So this got us interested in how we can make this process go faster. And in the burgeoning sub-area of machine learning called probabilistic programming languages. So these are tools whose goal it is to make it easy to specify some rich, complicated probabilistic model using the full power of the kinds of things we're used to having in deterministic programming languages. Good data structures and control mechanisms and abstraction, and you defined your model. And then the idea is that after that, the inference implementation comes for free. It's just provided by the library that knows how to work with your customized model to do the inference in the right way. FACTORIE is an example of this, but I want to put FACTORIE in the context of several other tools because this is a rich and growing area. And I'm not even going to list all of them, but just a small sampling of them. So a quite old tool that's been widely used by statisticians is called BUGS, which stands for Bayesian Inference Using Gibbs Sampling. And as it's an advantage, it handles arbitrarily structured graphical models. But it was never really designed for large data. It was designed for statisticians' small problems. So it's kind of small and only works on small data. There's an academic tool called Alchemy that comes from the University of Washington that has a very convenient, concise modeling language. Although I haven't used it myself, but from people that I've talked with, they're finding that it sort of has unpredictable efficiency and has been tough in that way. There's GraphLab, and I know we have people from GraphLab here, and so this is a delightful, super scalable, parallel distributed set of primitives that are based on computation that sit in the nodes and on the graph and on the edges of the graph, and has some great advantages. The primitives, however, sort of like the primitives of MapReduce, are defined separately from any machine learning considerations, and so they're not especially tightly intertwined. Although I understand that the tools there are getting built up with an increasing number of machine learning models. And then there are other quite different tools, like the Stanford Natural Language Processing Toolkit, which in academia, anyway, is one of the standard tools that are used for natural language processing. And it's been extensively developed over a long period of time. It has a very rich set of natural language processing data types and models. But it's kind of an ad hoc collection of multiple implementations, all separated from each other, without some unifying principles that would make it easy to build, say, a slightly different NLP model by composing pieces of other models together. So FACTORIE, one of the goals of FACTORIE is to try to get the best of all of these options, to pull them all together. So I really want to make sure not to just give you a positive sales pitch and to tell you about some of FACTORIE's shortcomings as well. So let me describe those also in terms of some other tools. There's another academic tool from Columbia called STAN that does Bayesian inference using sampling. And it really emphasizes and does a great job of inference on real values, real valued variables. And FACTORIE really, although it has the capability to represent them and has a few tools for handling real valued inference, our emphasis so far has only been on discrete data. We could develop out this area in the future, but it's not done right now. STAN really focuses on this Markov chain Monte Carlo kind of sampling methods to do its inference. And to my knowledge, does not have variational inference or message passing inference. OK, then there are tools like Mahout. that has Hadoop, that will scale in very nice ways. And FACTORIE, although we've applied it in various scalable distributed ways, say we've run it distributed across 1,000 machines to do some integrated inference problem, it doesn't yet come with pre-built tools that make it easy for you to do that. A student of mine rolled their own distributed arrangement in order to make this work across 1,000 machines. And Mahout's going to do a better job of that. On the other hand, well, it's Hadoop, so I don't know what you want to say about it. Draw your own conclusions. Scikit-learn is a delightful toolkit for machine learning, and it's just super mature, has gorgeous documentation and graphics built in. And FACTORIE is just barely 1.0, has no graphics integrated, and actually, the documentation in FACTORIE could use quite a lot of work, actually. Scikit-learn is in Python and C, and is kind of implemented as a bag of methods that don't necessarily, their implementations don't necessarily have too much to do with each other. Vorpal-Wabbit is a fantastic tool for large-scale classification done by John Langford. It's written in incredibly tight, efficient C++, and FACTORIE is just less efficient than that. Part of that is due to C++, part of that is due to just John Langford's brilliance in some of his tight coding. Vorpal-Wabbit is really built for binary classification, and that's what it does as its core. It provides some tools for doing things like multi-class classification, but it's actually, it takes multi-class and divides it into multiple binary classifications to get there, and we're striving to solve a much larger suite of problems. Okay, so let's get into further details of FACTORIE with just a, yes, please, thank you. Sorry?
You also cover the differences with mallet?
Let's see, I guess, thank you for it more accurate. There are a few very special cases of things that mallet does that are not currently covered in FACTORIE. Those include things like finite state transducers with a very large number of states that may have very sparse transition matrices, and FACTORIE doesn't keep track of that sparsity and leverage that at inference time, but that's actually something I want in some of my own work, so it's something I'll probably be adding in the next few months. Yeah, thank you for the question. I'd be happy to have other questions too. So it loosely stands for Factor Graphs Imperative Extensible. It's implemented as a library in Scala, as you know. We chose to implement it as a library, not as a new separate little language, because this lets us write our models right in Scala. It lets us integrate the code that we write for data preprocessing and evaluation and diagnostics right in the same file and language in which we write our model specification. And it lets us leverage object-oriented design for defining how the model works and how you can, I don't know, extend or modify through inheritance various parts of the probabilistic model. It's object-oriented in that all of these things are implemented as classes and as objects that can be changed through inheritance. Variables and factors and inference methods and learning methods are all objects. It's flexible in that it, unlike some of the other tools I talked about earlier, it can handle both directed and undirected graphical models, both variational or message passing style of inference and sampling styles of inference. And it's scalable in our experience anyway so far. Like we've run models with billions of variables, ones with a super exponential number of factors that are actually never instantiated before inference starts, but only like instantiated on the fly, on demand, in just the little places within the model in which that's needed. It's been plugged into a MongoDB backend to run on more random variables that can fit in memory. And although it's maybe not as fast as Vorpal-Wabbit, it's reasonably efficient in classification, sequence labeling, and a lot of other standard tasks. And it's released under a license that you can use in a corporate environment. The special sauce that I think about here is that some other tools, like Microsoft Research Infer.net, which I didn't describe earlier, but is also a fantastic package for inference and graphical models. Like Infer.net is incredibly powerful, but inference in Infer.net is just a black box. It's actually handled as a compilation process to, so it sort of compiles the model into code specific to your inference request. And my experience or understanding is that if you want to modify the way inference works here, because you have your own ideas about how to do inference a bit better, forget it. It's pretty much just penetrable by its original architects. Whereas FACTORIE is designed, hopefully, to make it easy for users to descend gently in layers of abstraction. Like if you don't know any machine learning, you don't know how a topic model really works, but you want to use latent Dirichlet allocation, there's already a pre-built one that you can just call from the command line, as there is in mallet. If you want to use a model that mostly pre-exists and just change a few little things about it, you can probably write just like a little 10-line script that will to get the components you want and plug them together in a slightly different way without too much difficulty. If you want to make some more significant modifications, maybe you write a 100-line script and get what you want. Or if you want to, all the way at the bottom, implement your own new inference algorithm that somehow works in concert with the other existing inference algorithms, you can get there again by, you have to learn some more. It's a bit more complicated, but it's not like falling off of a cliff. OK, so when you write a model in Factory, what does it look like? It comes in certain distinct stages. And in part of our architecture, we designed these to be very distinct in order to get a certain kind of flavor of modularity in the way we as machine learning people define our models. The first stage is to define templates for your data. Or think of these as classes of random variables that are going to hold the data about which you're going to be reasoning. And here you can actually often use data structures like you would in deterministic programming. So in ways that you would think would be kind of strange for a graphical model, you can have random variables for things like sequences or sets or things like this. OK, so then you load your data into these. And now you've essentially defined your problem in a way by loading the data in. You have a way to express both the input and the outputs. The next stage is you define templates for the factors. Or this is the model, right? This is how you're going to express which values in concert with each other do I think are the ones that would score most highly or the ones that I would prefer. And this is very distinct from the above data representation, making it easy for me to define my problem once. And then if I want to brainstorm about different alternative models, I can just change the localized code for that without changing the earlier one. So I write this part. And then I select some inference method. Then there's a large suite of different inference methods already provided. Then I select some learning method, about which I'll talk a bit more. And then I just write code to read in the data, create the random variables, and then inference and parameter estimation are often one-liners. OK, so I want to show you some code. And I'm almost there. But let me actually show you the names of some of the classes along the way. Will give you a broad sense of what the architecture looks like or what's available. All the words that I'm about to list are all actually the names of classes in Factory. So there's a variable, which is what holds your data. And a variable has a value and has a method for setting the value. And many variables also have a domain. So a domain is something that can be associated with a variable that essentially says something about, well, what's the set of values that are allowed in this variable? Then there are various kinds of labels, or actually traits, on variables. So like a labeled var is a kind of variable that also has a human-defined true target value. And we would need to use this during training to know the true value that we should be using in our objective function. There are things like diffs and diff lists that help us, almost like a transaction, make Markov chain Monte Carlo change to the world. And then if we want to reject that proposal, we can undo and roll back to where we were before. There are factors, as I've described before. There are things like families of factors that are a repository for sharing many pieces of things like parameters that would be shared by many factors. There are templates, which are ways to create factors on the fly according to some certain recipe. There are models, which is a source of factors, given their neighboring variables. There's a marginal, which is the result of inference, like a distribution over just a smaller set of variables, marginalizing out the other variables in the model. And then there are inference methods. And then there are three things that I'll talk about later: optimizers, examples, and trainers. And so we have various kinds of variables for holding everything from just integers to tensors, like vectors and matrices, sequences, even random variables whose values can be Scala pointers, which is what a ref variable is. OK, so let me talk about learning, and then I'll show you some code. So here's the classic, very general equation for learning. Theta is the set of parameters over which we'll operate. And I want to find the parameters that score the best according to some loss function and some regularization. So sets of parameters, like our parameters, may be spread across many different factors and many different factors of families. And there's a weight set is something that pulls together all of those parameters so that they can be treated as a whole by the inference and learning algorithm and preserves their mapping back to the factor families from which they came. And this is what enables Factory to Yeah, to apply essentially the same learning code to many different kinds of graphical models of many different structures with different numbers of variables spread across different factors in different ways. Okay, then all right, we need to search across the set of parameters that will minimize our loss function, and that's done by optimizers based on climbing some gradient. And there are various methods of gradient hill climbing, like conjugate gradient, a pretty classic one that you'd learn about in school, to things like LBFGS, which is a quasi-Newton fancy gradient climbing method that can work better, as well as some very fancy high-performant online methods as well. Okay, then we have the loss function. And these are encapsulated by what we call an example, which is a little wrapper around a little piece of data. Think of it as like, I mean, in the case of IID classification, it would just be the one email message and the one label that I'm trying to predict it as being spam or not, or it could be a whole chain for a linear chain CRF for doing Chinese word segmentation. So that data is wrapped together with a model and with a loss function that can deliver a gradient. The job of an example is to give a gradient that will eventually go into the optimizer. And the thing that sits between optimizers and example is something called a trainer, which is essentially responsible for essentially scheduling the different examples and how they move into the optimizer. So for example, in batch training, you would take all of your examples, get all of their gradients, sum them all together, and then in one big chunk give that one gradient to the optimizer that will take some step in that direction. But often it can be faster to do online training, in which I get the gradient just from one example, give that to the optimizer. Even though it doesn't really reflect the global optimal direction overall, it still tells me some direction to go that will be beneficial somehow, and it may zigzag my way to the best place, but I can make a lot of progress rapidly before I've even finished going through all of my data. And FACTORIE allows us to mix and match these things in a way that's very flexible. That's going to come up when I show you code. Okay, so here we go. Let's look at some code. And I'm going to follow through a suite of different kinds of models, aiming to show you how easy it is to mix and match some pieces. And let me say also that I'm showing you building a model in a very raw sense. And in a lot of cases, if all you really cared about were classification or linear sequence labeling or a topic model, those things are already pre-built, and you wouldn't need to get into any of this complication. It would just be provided as a one-liner. But here's what it looks like at a more raw level. Okay, my first stage is I need to define some classes to hold my data. So I'm going to build a binary document classifier here that's just going to say yes or no to spam. So I need one random variable to hold my document, and here it is. And it's going to be a feature vector variable. So it's going to store essentially counts of words that appear in the document. And then my other kind of random variable is a label. And it's a Boolean variable. It can be either spam or not spam. And because I'm going to need to train on it, it'll be a labeled variable. I'll know it'll be able to hold both its current predicted value as well as what its true value should have been. OK, and that's all I need for my data. So what's next? Well, I guess somewhere else I'd write some code that then knows how to read my raw data in off of disk and then create all these random variables. And that's what I will have done here. I'll get back a collection of labels. And each label is actually connected to the document that's associated with it. OK, now I need to define my model. And the key abstract method in model, so the model is going to need some factors in order to produce these scores. And here are the two relevant factors I would want, the compatibility between the spam label and my feature vector, that's the email message. And I didn't draw this before, but it's often also helpful to have an additional factor that doesn't even look at the evidence. It only looks at the label. It provides a sort of bias. Well, in the absence of any evidence, most email messages are, spam or not spam, depending on your stream. OK, and then these are defining families of factors that say, here's one that labels neighbors just a single variable. Here's one that neighbors two variables. And they are factors that will produce their scores by doing dot products, which is what the dot part means here. And then the other abstract method I need to produce is one that, given a variable, will return the set of factors that touch that variable. So here's a function that's given a label, and it returns a list that includes just two items. One is a factor from the bias family, and another is a factor from the observation family. And I've just given them their proper neighboring arguments. And now I'm done. I've finished defining the model. So just as an aside here, and this will come out more later, I can define the structure of my model by writing procedural code here, which gives me incredible flexibility to implement some pretty complicated model structures that can be value conditioned and all kinds of things. OK, so now I want to do learning. I guess I'll start by deciding to do batch training and send my gradients into LBFGS, quasi-Newton gradient climbing method. And then I'll ask that trainer to process some examples that I'll create, and I'll create an example whose gradient comes from the maximum likelihood criteria using this label. And this knows how, using the model to get what it needs in order to produce that gradient. And then I can do inference to say, well, OK, on some piece of data, let's see what the model has to say about this. And yeah, OK, and this already is everything that I would need to train a binary classifier. So let's see, I've already made some change. Let's say I wanted to have faster learning by doing online training. I can just, here, before I had batch training, and I can just change this to online without changing any of the rest of my data or my model, and the rest of it will just work. So that could be faster. Even better than stepwise gradient descent might be to take that gradient and put it into AdaGrad. Which is a more clever method for gradient hill climbing. Or maybe another method called AdaGrad RDA, which uses an L1 prior, which causes many parameters when it would not hurt accuracy to automatically go all the way to 0. And actually, we use this to make our part of speech tagger only 10% to the size that it would have been otherwise without losing any accuracy at all. And again, I just had to change one little place in the code to make this happen. Let's say I want to train even faster, and I want to actually do training in parallel across many cores all at once. There's a method called hogwild that can make that happen. And again, without changing any of the rest of my model definition of the rest, I can make that change. Let's say that instead of doing binary classification, I want to classify documents into 10 different possible classes. I can say that I want a categorical variable instead of a binary variable, and not change any of the rest of my code, and it knows what to do with that. Let's say that I want to get my gradients from a method that knows how to do inference across a wide variety of models, including ones that that might be loopy or have a very complicated structure. And the sample rank is a way to do this. Again, I can make that one change. And then let's say that I want to actually operate not over single variables, but over sequences, as we would in the Chinese segmentation task. And so I guess here I've said that my data items consist of sequences of labels, not individual labels. But I still actually didn't. I mean, I've changed the model pretty drastically, and the rest of my training code just magically worked in this environment. This is not a great factor graph for that model in the same way as the first Chinese word segmentation model was. I have no Markov transition factors in here, so I can add them by saying, let me have an additional factor here that captures my Markov transitions, and then have my factors method step over the sequence of labels and create factors connecting successive labels in this sequence. And then I could do inference in all kinds of different ways again, without changing anything about the model, by Gibbs sampling, or by specializing the Gibbs sampler with my own subsampling method, or by MPLP, which is a message passing inference method, or by belief propagation. And again, this is all done by mix and match, including just wild, crazy, much more complicated models, like ones that don't just have a chain of factors along the sequence, but actually these extra long arcing edges that turn this into a loopy graph, maybe in a way that, for the sake of time, I'll skip over. OK, so now I want to get into what we do in NLP, and then I'll wrap up. First, let me just say that we have pre-built tools for classification, for sequence labeling, lots of parts of natural language processing, which I'll describe in a minute, for topic modeling, like latent directional allocation, that's actually faster than mallet, for word embedding. So for example, we can learn semantic capturing real-valued 300-dimensional vectors associated with words by training on the entirety of Wikipedia plus all of GigaWord, which is a large set of newswire articles on one machine in less than 6 hours. So I guess with that in mind, maybe I should tell you just a bit about efficiency. So here we are comparing against some other tools for just simple IID classification. So in a way, this is not leveraging FACTORIE's graphical model infrastructure much at all, but at least we want to be not bad in this face, in the face of some of these other tools. And the results are that we're kind of within one time within the speed of a lot of these other tools. except for Leon Botou's stochastic gradient descent, which which is just crazy. I mean, I know that's crazily engineered. But we never expected, actually. I mean, it's also written in C++ in the rest. And running on the JVM and really having this very general infrastructure, we never expected to be faster than the fastest. Here we are in comparison with some other sequence labeling tools. These are all essentially linear chain conditional random fields. And it really surprised us that we were even just within a factor of 2 of CRF Suite, which is a C++ tool that, again, was just engineered to death to be super fast. And one thing that I find interesting here is that although the time for one pass are about half the speed of CRF Suite, in the total time for training, we're actually dramatically faster than they are. And in a way, this is not just a simple, direct, fair comparison, because really it's a convergence issue. We converge faster. And this has to do with just the way that we set up our learning. But in a way, it just points out that having tools that make it easy to reconfigure your machine learning, to tune it in various ways, can really help you do things like get convergence issues right, and that these can make a bigger difference in the end. OK, so in NLP, we have representations for documents and sections of documents and tokens and subspans of tokens within a document and sentences. Mentioned like noun phrases, like David talked about, and entities for doing entity resolution, parse trees, and as well as tools for doing all the things on the right. And I might give a short demo of some of these at the end if there's time. A few months ago, we decided to compare ourselves in accuracy and speed against the Stanford Core NLP toolkit. And we did not expect to do as well as them, because they've been in development for a long time, and they're really tuned and written from the beginning, especially for NLP. And we were pleasantly surprised. So in part of speech tagging, we found ourselves to be more accurate. This is token accuracy, 96 versus 90, in the high 96s versus the low 97s. And in speed, about 4 times their speed. So we're running at about 110,000 tokens a second for part of speech tagging. In parsing, we found ourselves to be a bit more accurate and dramatically faster, like almost 2,500 tokens per second versus 47 here. And in NER, we found ourselves to be more accurate, not currently faster, although that's something that we're working on. And we also have a new research result that's actually a state-of-the-art in a particular benchmark data set that we've been working on just recently. OK, so I'm just about done. Let me just give you a little sense of speed here. So I'm going to train a linear chain conditional random field on the problem of named entity recognition. So within a Newswire article, finding the instances of all people, organizations, locations, and miscellaneous named entities. And this is on a data set that was part of a competition that was run in 2003. I participated in that competition in 2003, and using Mallet at the time, actually. And I remember to train on this data set with it took us about 8 hours to train our model. So let's see, I think I should have about 8 hours left here, right? Very good, before you all have to go. OK, let's see what happens. So let's start this training now. So it's going to first read in about, oops, oh no, how can I make this bigger? About 200,000 tokens of training data and about 50,000 tokens of testing data, extract all the features. OK, just first, it's first passed through the data of training and parameter estimation on, I forget, it's about 400,000 features. It's now made its second pass and is already up to 94. OK, that was its third pass. And OK, it's finished. OK, so we finished training a named entity recognizer on 200,000 tokens of labeled data in 18 seconds, got 95% accuracy on the test set, and then and printed out a bunch of diagnostics along the way. So here are a few examples of named entities that it extracted from just the first section of the data. So like Peter Blackburn is the name of a person, and Germany is a location, and the EU is an organization, and so on. And actually, so in this set, we actually got them all 100% correct. I guess in the previous pass, we were getting a few wrong, but by the time we finished the last pass, we got them all right. So that's a sense. I have other demos that I could show you, but I think I might be running over time, and I want to make sure I get to answer your questions. So let me stop here, take your questions, and we can. I could show you more demos if you like. Thank you. Yes. I'm sorry. Could you talk a little louder?
Once I construct a factor graph, how can I visualize it? Can I visualize the graph?
Yeah, so we have no visualization either for results or for the graph itself. You know, we have not designed FACTORIE, I think, for use by people who, I don't know, don't already know their machine learning and know what they're doing. Although, actually, no, your question is separate than that. You could know what you're doing but still want to visualize it. And but I'm sorry, we don't have any visualization. That would be a great sub-project. I would love to merge in a project that did that. Sorry, thank you. The question was, do we have any visualization of the structure of the factor graph? Yeah, and we don't. Yes?
Well, what's next? So you took mallet so far, you took this so far. Do you see
Yeah.
that there's going to be a next step?
Okay, yeah. So we're continuing with FACTORIE for quite a while. One of the next major things that I want to look at there is infrastructure for parallel distributed processing. So like I said, I have a number of students and others who have successfully used FACTORIE in large-scale, 1,000-machine parallel distributed environments and gotten great results. But they rolled their own infrastructure to do that. And I think that there could be some great advantages to building parallel distributed infrastructure really baked into the same library that knows intimately about the probabilistic model and can reason about how to distribute the data and the computation at the same time as it's reasoning about the structure of the probabilistic model. And in a number of pieces of research that we've done, especially my student Samir Singh, who's actually doing a postdoc with Carlos Gestrin at UW right now, found that reasoning carefully about the probabilistic model to decide how to do the distribution could make multiple orders of magnitude in difference in speed. So for example, we've done a lot of work on entity resolution or co-reference, say running on like 500 million mentions distributed over a few machines, and reason in a very tight-knit way about the probabilistic model and how the data is distributed to get some big gains. So that's one area. It's possible that if we have more users who, I don't know, are more like companies and less like graduate students, that more visualization or some other polish would be helpful. And maybe this is an opportunity for me to say that I'm super thrilled that FACTORIE is getting usage by as many companies as it is already, and we're always happy to have company users. And if you ever use FACTORIE yourself, don't be shy. Send me email. I would love to hear from you, hear about the problems that you're applying it to, and yeah, we'd be happy to try to help you as well.
Yeah, I have more of a high-level question. I'm building, my name is Street from Live Talking. We're building a sales virtual assistant. Virtual assistant for Siri, for salespeople like Siri, for salespeople. And say I use nuance with a speech recognition and it parses the sentence, and can I use FACTORIE to build that virtual assistant, according to my requirement?
Yeah, so that's a pretty high-level question. I mean, it's going to depend on how much you're going to cast all the rest of that problem as a probabilistic model and whether it's well-suited to this in particular. I mean, I could imagine some steps of that modeling problem that would be well cast as a machine learning problem, and then I imagine the answer would be yes. I'm sorry, so the question was, in building some Salesforce automation methods, would FACTORIE be a good tool? And I can imagine that it would be. I'd be happy to talk with you afterwards about the degree of fit. Yes?
It's a common pastime of functional programmers in Scala and other languages to look for patterns from abstract algebra, the monoid probably being used.
Right, yeah.
If I understand factor correctly in some other contexts, we can multiply factors, which would form a multiplicative monoid.
Yeah.
From the code that you showed, I don't know that identifying that explicitly would make much difference, but
Yeah.
it might come to the good.
Yeah.
Is that factoring you?
That's not something that I've thought about really before. Let's see. Sorry. The question was, a lot of people who work in Scala are quite taken with the monoid abstractions, and would that interact well with factor graph structures? And not in a way that's obvious to me off the top of my head, but that sounds like an interesting question. I don't know if there are people here who are interested in some of our thoughts about Scala itself, there's certainly a lot of things that we love about Scala that have really helped us. We've made extensive use of traits to fold multiple pieces of functionality into one place. Like a random variable that holds a token, well, it's a categorical variable because the token is holding a string, and those fall into the different categories in the dictionary. But it is also a variable that is the link in a chain of a sequence because it's part of a sentence, and we want it to be both at once. We've made use of implicit parameters as well, especially for these diff lists. So like when you set a variable, if there's an implicit diff list around, then we'll pick it up to automatically build up this transition structure or this transaction structure. We've made use of function objects to create some nice syntax for making generative models. We've used implicit conversions in a lot of places that have been really nice. And we've made extensive use of the cake pattern in building parts of our models and part of our inference methods and so on. Some things that we would still like from Scala is maybe just a little bit more efficiency. And I don't mean JVM issues, I mean some other things. A few years ago in the Scala mailing list, I remember some people talking with Martin about making things a bit more efficient. And part of the answer was, well, we don't want to do premature optimization in areas that won't really matter. And I feel like a little more optimization would no longer be premature. We're sometimes kind of scared to use the Scala collection library because it has some surprising inefficiencies. And there are multiple places where even just the old Java collection classes are actually significantly faster than Scala. There's no reason for that to be true. It shouldn't be true. It would be really nice if these things didn't box anymore, and I know people are working on this, but my understanding is that I don't get it for free right now. And then just like some more predictability. It's like we might think that, okay, I just want to call the signum method on this, and that's like that's a single instruction, right, on the CPU. But if you look at what Scala does to this, it boxes it. And this is just crazy. And so, and I understand how this accident could have happened, but yeah, some predictability would be nice. OK, let me collapse that. I would love to have constructor arguments on traits, if for nothing else other than to get a class tag for a type argument to a trait. There are numerous places where I really wanted to use that. And this was even previously discussed, I think sometime in the late 2000s, actually, but still hasn't arrived. And then another, maybe this is a bit esoteric, but something that I really would have loved in certain parts of the creation of our class hierarchy for factors and for models is a linearization of inter-class inheritance. So in this first sub-bullet, if you say trait foo2 extends foo1, and then the meaning of super.foo inside of that is determined by the linearization of the traits, the order in which many traits might have come. But that same linearization does not apply to class extensions. So if I in some inner class say foo extends super foo, where this is the inner class of some superclass, this super foo is not linearized according to the trait ordering. And this just really bit us. And yeah, anyway, so that may be a bit esoteric. Yeah, so I think that's all I have to say about that. Other questions? So I'd be super happy to, yes, thank you.
So Spark is now extremely popular in Scala Big Data, and
yes,
they came up with the GraphX library, and they claim to be able to implement any other graph formalism in few dozen lines. So I think they came up with a way to implement the GraphLab approach in 40 lines and so forth.
Nice.
So did you look at that, and how would that compare to FACTORIE?
Right. Okay. So I've not looked at this, but I should, and I guess I gather that the guy who conceived of Spark is supposed to be arriving at MIT sometime this coming academic year, and so I'm looking forward to having him as a neighbor. I guess without knowing the details, having abstractions for computation sitting on a graph is a very helpful building block for doing inference in graphical models, but there's a lot more to go on top of that. And yeah, I would probably be interested in determining whether the kinds of future work we want to do in FACTORIE for better parallel distributed infrastructure could be built on top of this. Yeah, thank you. Nice question. Oh, yes?
Is MongoDB the only option for
Okay, there is no special privileged position for MongoDB as a choice with FACTORIE. In a lot of our own work, we actually use MongoDB for serialization, but serialization code, say, for different pieces of FACTORIE is unlike Java, not baked into the classes themselves, but actually written externally, sort of like in the Scala pickling library. So it would be very easy to build parallel infrastructure as an alternative to MongoDB that did something else instead. And I know that there are some people who are using FACTORIE extensively who are instead building on top of a cumulo instead. Yeah, and I'd love to talk with anybody who would like to. I mean, I would be actually eager to have publicly available, advertised code with various different NoSQL backends that FACTORIE could interoperate with. Yeah, thank you. All right, I'd be super. So there's my email address. I'd be super happy to hear from any of you. Stay in touch. Thanks so much.